All right, so I would start. Welcome. So I'll just say a few minutes about Flexcompute and about Tidy3D. And the world of computing is different. One of the major development in the past several years has been this dramatic rise of the importance of AI. And that builds upon, on the hardware side, builds upon the shift in the computational hardware. So what we come to see is that the CPU performance has largely saturated. And as you can see from this graph, but you know that when you buy a PC as well, the clock rate, for example, is no longer improving as a function of time. On the other hand, the GPU, which is a completely different computing architecture, its performance is still in the stage of exponential growth. And this has been really underlies this very great improvement in AI software as well, and which has penetrated into very large part of daily life as well as science and engineering. So one of the opportunity here is that the same kind of hardware improvement that drive the AI will also drastically influence and the performance of science and engineering simulation. So what we would like to do, what we did or will continue to do in Flexcompute is to exploit this opportunity in the shift of computational hardware to do electromagnetic simulation in a completely different way. So it probably is not necessary to this audience to emphasize the importance of electromagnetic simulation. You see that in very wide range of applications in electromagnetics and in photonics and optics. And this is true both for cutting edge research as well as for a wide range of industrial application. Now, the ability to do efficient and large-scale electromagnetic simulation is essential for the further development of many of these areas. So we have, in the past several years, developed this package we call Tidy3D, which is the next generation electromagnetic simulation technology that leveraging both algorithm and software improvement, as well as the fastest GPU. So there are many aspects that we will talk about in this seminar that make Tidy3D rather unique. But I'll just emphasize that it is built entirely from scratch to take advantage of GPU. So it's GPU native. And we have also gradually built up a very powerful user interface that really now match the state-of-the-art commercial software and go beyond it. And in particular, is the combination of a very strong graphic user interface as well as the Python interface that enable advanced user to really streamline and program their workflow. So one of the important aspect of Tidy3D is that it's GPU accelerated. And in our case, we spend a lot of time to innovate both on the algorithm as well on the hardware cluster that we have in the computer to deliver this performance. So here is a paper that we have written in collaboration with NVIDIA that was published in Optics and Photonic News last year to highlight some of the important advantages of GPU, in particular for finite difference time domain simulation that underlying the Tidy3D. And one thing to note is that FTTD is a bandwidth limited algorithm and therefore benefit very significantly from the large communication bandwidth inside GPU. And as you can see in here, there's tremendous amount of performance improvement when we go to GPU as compared with standard CPU architecture. And one of the features of Tidy3D that you probably notice is that it's extremely fast. And we typically see orders of magnitude improvement compared with standard commercial code. Moreover, we are capable of dealing with very large number in reasonable time that are essentially not doable with other commercial solver. So one example is on the right-hand side of this graph, where we have a simulation of a three-dimensional simulation of a large-scale matter lens. These are hundreds of wavelengths in sizes and in dimensions, and with about 10 billion unknown, which you couldn't usually put with a commercial solver, but we can do that under an hour. So the ability to do these fast simulation also enables the ability to do design and optimization. And here in particular, we have incorporated very powerful inverse design technique based on adjoint variable method, where one can compute the sensitivity to large number of parameters efficiently to compute a gradient for optimization. And this is something that Tyler, who is going to take over me, I believe is going to start and to give you more information about. So I'll stop here.
Hey, thank you, Professor Fan. I will share my screen now. Hopefully it's visible. Can you see this title slide?
Yeah.
Yes.
All right. Yeah, thanks for the nice introduction. So this will be the main topic of the seminar. Again, my name is Tyler Hughes. So I'm going to be focused today on the topic of inverse design in Tidy3D, and I'll be spending the majority of my talk discussing our approach to designing a programming interface for inverse design through what we call differentiable simulations. And I'll talk about what that means, how it allows us to do very flexible, powerful, and easy to use inverse design in our platform. So before I do this, I want to touch on a few connotations or expectations that people often have when they think about the word inverse design or the term. People often think it's extremely complicated. They imagine there's all these algorithms, there's lots of mathematics involved, adjoint method, and it's essentially very complicated and hard to get started with. People also think, oh, it creates these devices that are kind of crazy looking, uncontrolled and unintuitive. And the last thing people think about is it's very slow typically. So you have to have tons of FDTD simulations. And if you're doing large scale 3D problems, people often think it's kind of infeasible. And the goal of my talk today is to show you that the reality is actually, the opposite is actually true with Tidy3D. So first, it's very easy in Tidy3D to set up and start doing inverse design optimizations. And the way we design it also is extremely flexible and controllable. So you can actually do inverse design with your own design parameters, with your own intuitive set of levers in your simulation or in your design problem. So it's very controllable. And the last thing is, as Professor Fan mentioned, it's extremely fast in Tidy3D. So that you can do problems that took weeks before, and you can do them in under an hour for inverse design problems. So as an introduction, my talk today, I'll first talk a bit about setting up or thinking about device design or photonic device design more mathematically as a mathematical optimization problem, which is kind of the way that you need to think for inverse design. And then I'll spend 2 sections talking about the concept of differentiable simulations. So first is I'll talk about a concept called automatic differentiation, which is how we compute derivatives of very complicated objective functions for inverse design. And then I'll talk about something called the adjoint method, which kind of connects automatic differentiation to the FDTD method to be able to efficiently compute the derivatives. And finally, I'll spend the majority of my time going through several demos and examples. We have a few dozen examples on our website of different inverse design for different applications, but I'll touch on a few of them. So first, let's talk a bit about the concept of photonic device design and trying to frame it as a mathematical problem. So most of the time, if not all the time, when you're doing a photonic device design, the way you can think about it generally is something like this. So you typically have a set of design variables or design parameters. So these are the things that you have control over in your design, such as geometric things like spacing between objects or the size of different objects. You might have control over the material properties or where the materials are placed in your simulation. And then you might also have some more abstract design variables, such as parameters that affect many things at once. But typically, these design variables are kind of the inputs to some figure of merit function, where these design variables ultimately set up one or more, they basically set up your device, right, or your simulation. So these design variables come in as inputs, they set up your simulation, and then you would use a simulation tool like FDTD to compute what are the electromagnetic fields in my device. And typically you're not interested in the fields directly, but rather taking the fields and then doing some post-processing. So you want to compute some measurable quantities of interest, such as maybe the transmission, the mode amplitudes, or maybe even some penalties that are determined by how your design variables are set up. But in general, you can think about everything in this blue box as kind of a function f of x, where x are the inputs, and f of x gives you the measurable quantities that you care about designing over. So try to abstract everything out and just think about design as this function f of x. As kind of a more concrete example, let's say you're designing a grading coupler like this. Maybe the x represents the centers and the teeth of each, or the center and size of each tooth. So you can actually have independent control over where you place the grading teeth. And then f of x might be the coupling efficiency of the output port. So you can imagine that the simulation of this grading coupler kind of defines a function f of x. And then your job in designing a grading coupler is really to maximize f with respect to x. So you can imagine it as a mathematical optimization problem now. So find the x that maximizes the coupling efficiency and potentially subject to some constraints. For example, I could say one constraint might be if the grading teeth ever cross, then that's not allowed. So all of inverse design can kind of be framed in this, this context. Now, once you've set up the optimization problem, then you just solve for f of x, so or solve for the optimal set of design parameters. And the most efficient way to do this, I mean, there are many ways to do this, but one approach that's simple and works is to use something called gradient descent. The idea here is you can imagine your f of x as a kind of search landscape where you're trying to find, in this case, maybe the minimum value of f of x. And a very simple approach is you start with some value of x, you compute the gradient of f with respect to x, which gives you sort of the direction downhill, so to speak, in this search landscape. And then you simply move a little bit in that downhill direction, and then repeat this process iteratively. So compute the gradient again, move a little bit, and just keep repeating until you've converged on the best value. So this is called gradient descent, and this is actually the same way that machine learning models are trained, and it's the same way that inverse design is typically done. And one important note, which will be very important later, is that, of course, to do this, you need to be able to compute the gradient and not only compute it, but compute it efficiently. So we'll be spending a bit of time on that. Right, so we need the gradients. So we can imagine our simulation tool, just FDTD, as evaluating f of x, right? But now what we need is a way to actually differentiate f of x. So you want to compute df dx and rather get this gradient or maybe a Jacobian matrix of how all of my measurables change as I change my input parameters. And this is a map of the sensitivity, and this is what we'll be using to do inverse design, sensitivity analysis, and all sorts of different things. So again, bringing this back to this grading coupler example to see what I'm talking about, if x1, x2, x3, for example, are the widths of my grading teeth, then with the derivative information, I can compute how does my, how sensitive is my efficiency to the width of each tooth. And I can also then say, well, now that I have these derivatives, how can I move the teeth around to maximize efficiency? And that's kind of what we call inverse design. And the goal here, so, as an API or a Python developer setting up the simulations, the real goal of what I'm trying to set up is we would love to have a platform where we can set up our grading coupler simulation and just define our figure of merit in a simple function. So for example, what's my coupling efficiency as a function of the width of each tooth or the gaps? I can write some code that sets up my simulation as a function of these parameters, runs the FDTD efficiently on our cloud, and then does some post-processing to grab the efficiency. And the idea is with Tidy3D is you can write a function like this that computes the coupling efficiency. And then because of the way we've designed things, in one extra line of code, you can automatically compute the gradient of this function with respect to all of your design parameters, and then use that in your optimization. And it's worth noting that it's so flexible that if you add any of your arbitrary code inside of here, it will just work automatically with the derivatives, which seems like magic, and it feels very flexible and intuitive. And in the rest of the talk, I'll be kind of explaining how we accomplish this and then what we can do with it. Okay, so basically the problem is this, right? I set up what we want to have. So how do we compute derivatives of simulation design problems of arbitrary complexity in an efficient and general way? And the way we do this is through a concept called differentiable simulation. So the problem I said with it before with a gradient coupler is quite simple, right? It's something that you could maybe derive. If you have a day on your hands, you could derive it by hand, the derivative of that whole process. But in general, you might have something way more complicated, right? Like your design problem might have some parameters that set up one or more simulations. So you might have several types of gradient couplers with slightly different parameters. You might want to run all of these in a batch, compute the fields, and then do some averaging or some kind of complex operation, and then include maybe a penalty that's over your design parameters. So in typical inverse design and design optimization problems, it's not as simple as the example I showed before. It can actually be quite a complex pipeline such as this. So we need some way to handle arbitrarily complex figures of merit in a scalable way. Now, it turns out there's already a technique for dealing with these kind of arbitrarily complex computing derivatives or arbitrary complex functions like this. And the approach is automatic differentiation. Automatic differentiation is a tool that's used commonly in machine learning. Packages like PyTorch you might have heard of use this under the hood to train their models. Essentially, it's a fancy word for chain rule on a computational graph. So it's a generalization of chain rule to instead of just like a simple function to something complicated. So let's take an example. Let's say our function, forgetting FDTD or anything, let's just say we have this mathematical function here, sine of x times x plus cosine of x, and I want to compute the derivative of this with respect to x. Now, the one way to do this with a computational graph is to represent this as a graph, and you can say, well, I pass x in, and then every time it hits a node, it does some operation, and then I get f of x on the right. So it turns out to compute the derivative of this graph, all you need to do is you need to look at each of the nodes. So for example, sine, and you need to compute the derivative of each node. So I create a new graph where sine is replaced by cosine, cosine with minus sine, etc. And this is kind of the reverse derivative graph of this function here. And to compute derivatives, you simply start with a 1 on the output, because that's the derivative of the output with respect to itself. And you simply propagate this derivative information backwards through these nodes and then sum to the input. So in a sense, this is computing the chain rule at each step, but then it's back propagating all of the chain rule derivative information back through the network. And if you see this, if you're familiar with neural networks, this is essentially the back propagation algorithm for neural networks. It's all the same thing. What's really cool about automatic differentiation is there's tons of packages now such as AutoGrad is one, that let you do this in Python code. So when you write a function f of x, a tool like AutoGrad will know all of the derivatives for cosine, sine, multiplication, etc. And it'll be able to construct and evaluate these reverse graphs in the background. So as you execute f of x, it can construct the graph. And then when you ask for the gradient of f, it can return you a new function that does this whole process behind the scenes. And you don't need to derive any complicated expressions at all. So this is the tool we want to leverage for inverse design. The key is that, of course, AutoGrad or PyTorch, they don't know anything about Tidy3D or FDTD simulations. And in the kind of computational graph of your figure of merit, you're going to encounter some FDTD simulation, right? So the whole trick of Tidy3D is we said, well, we just need to define, if we encounter a node that is running a simulation, we just need to tell AutoGrad, for example, how to backpropagate the derivative information through that node. And once we've done that, then it enables what I showed before, and it basically enables you to write any arbitrary functions in Python with a crazy pre- and post-processing. And if there's a simulation run or many simulation runs inside of that function, AutoGrad is kind of automatically primed now to know how to handle the derivative of that operation. And so it can handle this function just like any other and give you the gradients back. And so this lets you set up, kind of plug in Tidy3D into the whole AutoGrad and automatic differentiation framework. So that's a bit of background, but now we want to talk, this is important for, all of this stuff will actually happen behind the scenes when you're using Tidy3D, but I think it's important to understand what's going on underneath the hood so that you can kind of have a deeper understanding. So how do we actually compute the derivative for an FDTD simulation? That sounds like kind of a abstract and sort of a hard task. So actually the way we do it is through a mathematical technique called adjoint method. So the adjoint method essentially lets us backpropagate through a linear system solve mathematically and in an efficient way. So what does that mean? So let's say that we formulate our EM problem or our FDTD or FEM or any problem as a linear system like this. So A would be a matrix that kind of contains all the information about your device and the system. X represents the solution, so the electromagnetic fields in the situation in the system, which we don't know yet. And then B is a vector that is just the source, so it's kind of the current source is driving the system. The design parameters are, of course, like our geometric and material parameters affect the system matrix. And then the figure of merit that we want to differentiate at the end is a function of the solution X. And it can be a function of P too, but for now, let's just pretend it's just X. So for the derivative calculation, what we really need is ultimately, how does our figure of merit depend, or what's the derivative of our figure of merit with respect to the parameters, not X, but actually the parameters. So to do this, you need to take a derivative of the linear system solve, or of X. And if you do the chain rule, this is the only time you have to do the chain rule, but if you do the chain rule, you get this expression here for the derivative, right? It looks a little intimidating, but it's worth breaking down what this means. So this expression includes the change in the system matrix with respect to each parameter. So for example, if I move a waveguide, this would select out the area that got changed from that parameter change. It involves critically the original electromagnetic fields from the kind of original system that you're solving. And then you have this kind of ugly term here. And the key with the adjoint method is to just group this term on the left together and identify it as just another field solution. So another electromagnetic simulation solution, where now you have the same system matrix. Well, it's transposed, but essentially the same system, but now the source is replaced by this term here. So basically the source now is encoding how the figure of merit is affected by your measured fields from the forward simulation. I'll explain a bit more like the intuition behind this, but this is known as the adjoint source, and this entire thing is known as the adjoint simulation. So to solve the derivative, you set up and solve this adjoint problem. You get this x tilde, and then to compute the gradient with respect to some parameter p, you simply take this inner product between the adjoint and the forward solutions over the change in p. Now, the critical thing to realize about this is that both x and x tilde don't depend on p at all. So in a lot of inverse design problems, you might have millions of parameters, right? And you don't want to have to do an FDTD simulation for every parameter, which is what you'd have to do if you were doing a finite difference derivative. And what adjoint lets you do is you solve x and x tilde once, the adjoint and the forward problem one time. And then for every design parameter in your system, you can just perform this inner product. And typically this inner product is very cheap to compute. So it lets you essentially get an extremely large dimensional gradient, like you can do a million dimensional gradient or more with just 2 simulations, which to a lot of people sounds like magic, but if you go through the math, you'll see that it's true. There's still this inner product operation, but it's typically quite cheap, like a summation over of the fields over some region. Okay, so this is really what the missing piece that lets us do inverse design and gradient-based optimization. Just to kind of drive home what the adjoint means. So if we're doing some kind of, let's say, a waveguide bend problem where we're optimizing this middle region to transmit from left to the bottom waveguide, the original simulation might look like this, right? And because we're measuring the fields at the output port here, the adjoint simulation would place a source where we're measuring our fields and then it would inject a source back into the simulation where the source phase and amplitude are proportional to this df dx. So in some sense, the adjoint source can kind of encodes all of the derivative information coming from downstream in the graph. And once you've solved these two fields in the design region, you can compute these inner products to kind of perturb your design region in the gradient direction. So as I mentioned, users don't need to know anything about this. When they run Tidy3D, you'll just need to know that you'll see an adjoint simulation get run automatically. But just to show you how automatic this is, basically, if I'm, in my previous example, I had this function, if I ask AutoGrad to compute the gradient of the function, what's happening behind the scenes is this. You'll run your function, you'll see a simulation kick off, and the data will come back, and then the figure of merit will be processed, and you'll get the value. But what we do is essentially we store the fields in the design region that you want to optimize automatically. And then if you ask AutoGrad for the gradient of this function, what it does is it starts to do the backpropagation. Once it reaches the FDTD part, it constructs the adjoint simulation automatically. So it sets up all the sources, sets up the adjoint simulation, runs it behind the scenes, stores the fields in the same area in the design region. And then once we have that, we compute this inner product, we get the gradient, and then we essentially package it for AutoGrad. And then AutoGrad says, thanks a lot, and it continues with its gradient calculation. So it's basically, we've plugged all this adjoint stuff directly into AutoGrad so that it happens behind the scenes. And when you ask for grad, you just notice one more simulation kicking off, and then your gradient gets spit out. So it's essentially a seamless process. And again, what's really nice about this is it's so general that we can just define the adjoint rule for any general problem, right? So any general FDTD problem that we can encounter in Tidy3D. And that means that we can implement all these sorts of features, right? Like from field projection, different types of optimization, everything's kind of automatically supported because we've done it in this general way. Whereas a lot of our competitors' approach to inverse design is to kind of give you only access to like one specific functionality. And then if you want something more general or different, you have to kind of request it. And the way we've done it, it just gives us the ability to really produce all these features very quickly. Now, that's a lot of like kind of complication for a lot of people. That's maybe too much information, like having to do with this the functional way. So we decided to also provide a higher level API. So if you don't want to get involved in the functions and AutoGrad, and that sounds too complicated, we also let you design your inverse design problem in kind of a high level API. The idea here is you might have some regions that you want to design or optimize. So you can simply at a high level specify these regions. So for example, if I'm doing this waveguide bend, I might say that this gray box is my design region. I'm going to split it up into a bunch of pixels, and I want the pixels to go between, let's say, air and epsilon of 4. So I can set that up very easily. And I can even add things like, feature size, like a tunable feature size constraint to kind of make sure that the final result is fabricable, and I can define a objective function without having to touch any of this Python functions or AutoGrad. And essentially this kind of object-oriented design is nice because in the background, it constructs that function the automatic differentiation will use to compute the derivatives, but as a user, you don't have to worry about it. It's worth also noting that we have this, as Professor Fan mentioned, we have this graphical user interface, and we've included these inverse design tools directly into the graphical interface as well. So you can basically set up these high-level inverse design problems in the GUI. So for example, I can take a simulation that I've done in GUI or done in Python and upload it to GUI, and then simply add a design region into the GUI or into my simulation, hit optimize, and then see in real time as the device starts to optimize. So that becomes a very powerful approach if you want something that's kind of ready to go, and you can add this to any of your simulations right away. And we're also adding many new features to this high-level wrapper and the graphical user interface in the near future. So I hope that gives you a general overview of how this works. I think the next section I will talk a bit, I'll just show a few examples to show you what we are able to create with this tool. And the goal is just to kind of inspire you to think of new ones. And if there is something I haven't touched on, feel free to ask in the Q&A because we have a lot of other examples I can't show. So it's possible I can just load up something from our documentation and talk about it if there's a topic that you're especially interested in, such as a photonic crystal or something like that. I won't touch on that here, for example, but I can in the Q&A. I'll just give a brief flavor. So yeah, we have a lot of notebooks, maybe about half are related to this topology optimization idea. And the idea here is that you kind of take a design region, some part of your simulation, you split it into a bunch of pixels, and you say, I want to optimize so that each pixel can vary between two permittivity values, so maybe like air and silicon, for example. And I'm going to create this image almost of my device in this design region and optimize the material parameters at each point. So this is a very common approach for inverse design. Well, it's what people often think of. So in this case, I'll just show one of our topology optimization examples with a waveguide bend where we're trying to couple from this green source to this orange monitor. And this is, again, just a note, like all these problems are 3D, or most of them. So these are quite large problems. And I'll show you how fast they are in a second. But yeah, so of course you start with a kind of somewhere halfway between the material and air, and of course the device doesn't work at all. And then if you run the optimization, you'll get a device that looks like this. It looks quite unintuitive because topology optimization often produces these kind of devices. But you can see that we add some constraints and feature size constraints in there so that this device could be fabricable. Now, we can achieve this device. What's really nice is it took us 30 minutes, or I think 35 minutes to do this entire optimization. This is a 3D problem. And we did a benchmark. If the same problem were to be done on a CPU-based FDTD, it would easily take over a day just to get this result. So you can imagine you can do dozens of these kind of optimizations on Tidy3D in the same time that you would take to do this on a conventional FDTD solver. So that's quite powerful because it lets you iterate on your design ideas a bit more. You can inspect the intensity pattern. You can see indeed that the fields are coupled, or the light is coupled to the bottom waveguide. And then you can do post-processing or some analysis and look at the spectrum. And there's even a lot of tools in the inverse design plugin to do a broadband optimization. So if you really wanted to increase the broadband coupling, you could, let's say, do the average over many frequencies in the simulation. We have other topology optimization examples. This is a slightly more complex one. This is showing off the kind of broadband objective idea as well. So this is a wavelength division demultiplexer. So you can see the idea of this device is if I send light, for those who aren't familiar, in the input port, I basically want light of different wavelengths to come out at different output ports. And you can see, in fact, all of these different wavelengths do couple to the proper output ports. And the objective here is kind of interesting. It's a bit more complex. And this is the beauty, again, of this approach, is that we basically said, well, within these blue bands, if your blue band matches your port, then we want to maximize the transmission in that band, like sum it over the band. And otherwise, if you're outside of your port, we want to essentially suppress the transmission. So you're able to write a very complicated sort of objective function here about the insertion loss and do this optimization. And it's also worth noting that this is like involving a multi, this is maybe a multi-simulation problem as well. So like simulation batching and simulation, parallel simulation running is also completely compatible with this whole approach without any addition. So this is a quite nice demo. I recommend you check this one out as well. We also have a notebook that applies fabrication constraints or more advanced machine learning based fabrication constraints to this problem. So there's a follow-up notebook if you're interested in these kind of problems. Another thing that's really cool is that we can do multiple design regions in a single simulation without any problem. So we've done a few. Here's an example where we're doing a grading coupler. We have a silicon nitride layer that we do topology optimization, this red region. And below we have a blue silicon region. And we're basically just consider the set of design parameters is twice as large here. And we just kind of co-optimize both of these regions at the same time. And by doing this dual kind of optimization, you can get much better results than you would be able to with just one design region. And of course, you can add other ones as well, such as pattern of the back reflector or something. So it's a very powerful and flexible technique. Another great thing is we've done topology optimization with dispersive materials. So instead of just interpolating between like a epsilon of 1 and epsilon of 4 or something like that, in this example, we actually we did a plasmonic nanoantenna optimization and with topology optimization. And what we did is we said we took ellipsometry data from gold. So we basically took the measured N and K values for gold as a function of frequency, fit a dispersive model to that data. And then we say, well, we're going to do optimization, but we're going to basically change each pixel between air and then this dispersive model. So we do some linear interpolation between a metal and air. And it's really cool because then you can evolve these plasmonic kind of devices like this. So this is actually like enhancing the focusing efficiency here. So kind of designing a bow tie antenna. And this is something that's a kind of a state-of-the-art technique in topology optimization. A big one too, the other kind of main class of optimization is called shape optimization. Now, shape optimization is arguably even more impactful because it leads to more intuitive devices and more intuitive design parameterization. So we have many examples of shape optimization. The way it works here is instead of changing the material at each pixel in the device, you actually just parameterize your geometry and you say, I want to optimize with respect to the boundary of my device, or let's say I define a polygon. So in this example, I have a taper on the right. You start with a linear taper that's defined as a polygon, so it's kind of discretized. And then you say, I want to optimize the taper for transmission, but I'm going to let the polygon vertices move around in maybe a controlled way or in whatever way you define. And it will kind of automatically use the adjoint method to figure out what shifts in boundaries lead to more improvements in objective function, and you can even apply more complicated parameterizations, such as a fits spline, a spline fit, or things like this. So it's a very powerful technique that we've applied in a few ways. Here on the left is showing a silicon nitride waveguide bend. Another kind of example of shape optimization that's even more intuitive is the grading coupler, and we've done many of these kind of simulations. Here we have these rectangular grading teeth. You can do this with also curved, like focused grading, so like curved grading teeth. But basically, like the problem I described at the beginning, where your design parameters are now like the position and the width of each tooth. And Tidy3D can kind of compute automatically how these teeth need to change centers and widths and how the gaps need to change to maximize the coupling efficiency. So we did an interesting study, again, it's linked here, where we, so and also you can put constraints, of course, like crossing constraints. We did an interesting study recently where we took a grading coupler and we simulated a uniform grading coupler that was kind of the optimal uniform device. We starting from that initial condition, we just said, okay, let's let the grading teeth move around and get bigger or smaller and essentially see how much of a performance improvement we could get. And we actually saw a pretty modest improvement or pretty good improvement in both the coupling efficiency and bandwidth. And what was interesting is it looked like an apodized grading coupler where the teeth were actually getting smaller as you move along. So we then loaded up an apodized grading coupler design in orange here, and you can see we basically get the same performance, maybe better bandwidth. But what was really interesting is that you can see here, I'm showing the optimization. This is obviously sped up, but the teeth moving throughout the course of the optimization. And if you look closely, you can see that the inverse design technique actually converges on the apodized grading coupler design, or at least some version of the apodized design that's maybe has a higher bandwidth. So this was a very kind of cool study. And again, it just uses shape optimization with simple geometric primitives. Okay, last couple ones before I'll say, yeah, another example of shape optimization is, you can do complex geometries like cylinders or, so for example, we've done a meta lens simulation. Our optimization, we start with cylinders and all uniform cylinders, and we just optimize the radius of each cylinder to maximize the focusing efficiency. And you can do the same thing with, let's say, photonic. We have an example with a photonic crystal where we optimize the whole positions and the whole radius in the photonic crystal. So I've talked a bit about the device parameterization, but another equally important thing is the outputs, like how can you process the outputs of your simulation? So we can do a lot of interesting things here. So, and a lot of general things because of the automatic differentiation ability. So one thing we did here as a demonstration is a very crazy looking meta surface. Basically, we set up a meta surface with topology optimization, and we said, well, we wanted a meta surface that creates our Flexcompute logo at some distance above the meta surface. So this objective function is kind of weird to think about, but basically we take our logo as a file, we load the file, we convert it into an array, and we take like the inner product of the Flexcompute logo with the measured near field intensity, and we use that as our objective function. So just to kind of show off how general it can be, and you can see that to good approximation, it is able to kind of reproduce our logo, which is quite cool. And kind of along the same lines with field projection, there's a lot of Tidy3D offers all these sorts of field projection methods. So from near to far field, with approximations if you would like, or also with you know, just raw or sort of exact field projection using the free space Green's function. But yeah, we have an example where you can use a gradient coupler and you can optimize the far field projection. So you can ask the gradient coupler to kind of project to different angles, and you can move these angles around at will using the near to far field transformation. So this really helps cut down on the size of the simulation that you need to optimize and simulate. And finally, I'll just kind of, again, show off a little bit of the flexibility here. We've done multi-objective and multi-simulation studies. So in this example, we basically had a device we want to simulate where we wanted to work as a Mach-Zehnder interferometer. So we said, well, we have two components. We basically have a splitter and a combiner kind of component. At least that's what we want them to do, but we set them up in a general way. And we have two Tidy3D simulations going then, separate and totally independent. And we categorize these, or we do a simulation where we compute the scattering matrix for each of these simulations. So that kind of allows us to then hook everything up into a circuit model, right? So in this case, we use a circuit model called SACS, which is a differentiable circuit simulation tool. So what we did is we defined a circuit level objective. We basically said, if I put an input to this circuit here, if my phase on one of the arms is 0, I want it to come out of port 0. And if the phase is pi, I want it to come out of port 1. And defining things, our MZI in this way, and using the gradients and all the backpropagation to handle everything automatically, we were able to optimize each of these components at the same time within the circuit. So you can imagine for very complex devices, this can be very powerful. Yeah, and another thing, like the last thing I'll mention is this similar technique can be useful for doing sort of a robustness criteria in your optimizations. So for example, you can simulate ensembles of simulations under certain conditions, like an eroded and dilated version of your simulation. And because of this tool's parallelism, you can have all these optimizations or these simulations running in parallel, and their results are kind of averaged or combined together in the output. And you can do a lot of interesting kind of robustness verification for your optimizations as well. So I think with that, I think I've hopefully convinced you of a lot of the interesting things you can do with this tool. We do have a long Q&A session, so I'm happy to kind of go into more examples, more details, answer whatever questions you have. If you're interested in kind of learning on your own, we have a very extensive documentation. If you search Tidy3D docs, you'll find it, but the link is here too, including all these examples, which are available to just download and run. So everything is kind of in code. And then finally, if you want to learn more about the kind of the theory behind inverse design and some of actually also the practical tips and tricks that I couldn't get into here, we have a set of inverse design lectures led by Professor Fan, actually. And these lectures go into all of the details of kind of the theory behind inverse design, more details on the adjoint method, and then some like practical tricks and tips for setting up your inverse design problems and yeah, like accomplishing your device design. And there is a lot of kind of knowledge in there, like intuition, that it is helpful to get a little bit of experience before you just jump right in, because it can be a bit complicated and it's more of an art than a science in some way, doing this inverse design. So yeah, I'm happy to answer your questions in a bit. the way this will work is we'll have Prash take over for the next 5 minutes, and he's going to just give you a bit of a sense of what other products we are working on in the meantime, and give you a high-level overview of some other things you might be interested in. And during that time, we'll be collecting the Q&A questions, and then we'll just kind of jump right back, and I'll start answering your questions. And the other panelists will also be answering your questions in text form while we do that. So anyway, thank you so much for your attention. Look forward to answering your questions in a bit.
Hi, everyone. Can you guys see my screen?
Yes.
Okay, great. Yeah, thanks a lot, Tyler, for that really nice talk. So I'll zoom back out a little bit and talk a little bit about Flexcompute and all the different products we have. And so you guys already saw how, being able to run really, large scale FTTD simulations much faster already allows you to do pretty complicated, optimizations. So I'm gonna kind of skip this part because Professor Fan already covered this. So at Flexcompute, we have the EM side of things, but we're also used to simulating, a very different physics. We have products for thermal simulation. We have a big team working on computational fluid dynamics, acoustic solvers. So our products are already being used across very different industries, all the way from aerospace and defense for aircraft wing design to interconnect simulations for let's say data centers, right? And because of this, we're already used to simulating very different physics, all the way from fluid dynamics to photonics, and even more recently charge and RF solver. And the reason why I wanted to kind of bring this up is when you're trying to build a real photonic chip that that goes into production, or when you're trying to commercialize a photonic platform, you actually end up doing a lot of different simulations. You end up doing optical simulations at the component level. Let's say you might be using an FTTD solver, mode solver, EME solver. You might be doing inverse design optimization. You might also be doing a lot of RF simulations. You might be optimizing your transmission lines, interconnect simulations, wire bond simulations, signal integrity analysis. And then also, when things are more complicated, like heterogeneous integration, when you have co-packaged optics, you might be running component level thermal simulations, or even thermal simulations at the module level. And then, a big part of a lot of devices that actually end up being used in the real world are actually active devices. So there you might want to run electro-optic simulation, charge simulation. So currently, if you want to design a full photonic chip, the workflow is pretty fragmented, and there isn't really a unified platform for doing this multi-physics simulation. And that's something that we're, increasingly addressing with all the solvers that we're building. So here, some of the products that we have released under our Tidy3D brand, we have our FTTD solver, we have our mode solver, EME solver. We just released a new software that allows you to do end-to-end photonic design, all the way from layout to circuit simulations and loading foundry PDKs. We call that Photon Forge. We recently also released a charge solver, and then we have a heat solver that's already been released last year. And because we're rewriting a lot of this software from scratch, it allows you to kind of rethink how we build our solvers, how we make it multi-physics, and RF is another big part when you do active device design, and this is also something that we're working on. So just to kind of briefly introduce a few of these new products that we've released. So Photon Forge is our next generation photonic design automation platform that allows, that seamlessly integrates with our GPU accelerated solvers to run multi-physics simulations. So you can go from, doing a layout of a chip to, doing a full circuit level simulation. We support a lot of different foundry PDKs. Here are some of the ones that we can actually put in these slides. We work with foundries across USA, Europe, and also Taiwan. Here, we have PDKs already for Tower, IMEC, Fraunhofer, HHI, Luxtelligence, Ligentech, AIM Photonics, and the idea was to kind of demonstrate that our software is flexible enough to handle very different material platforms. So if you're interested in any of these PDKs, those come free with our software, and it's really easy to also build your own custom PDK. Another big part that we're focusing on is also trying to bridge that gap between photonic simulation and also RF simulations. Especially, one thing I realized is a lot of people from photonics background don't really end up doing a lot of RF simulations, but RF simulations are pretty critical if you want to build a working device. And so we are integrating both the optical and RF solvers through our platform. We have a lot of example notebooks to show you how to design, for instance, a Mach Zehnder modulator, high-speed Mach Zehnder modulator in thin film lithium niobate platform. We're also doing an Optica industry seminar and this month, if that's something that you guys are interested in learning more. And then, if you really want to start simulating active devices and looking at the performance at system level, you also need to be able to do, circuit simulations both in frequency and time domain. So we built those capabilities now. So you should be able to, look at eye diagram, look at bit error rates and stuff like that. If you're if this is something that you're interested in. And then more recently, if you're trying to design a active device in silicon photonics platform, you do need to solve Poisson diffusion equations to let's say to design your modulator. For instance, if you want to know how does bias voltage affect the effective index change in your waveguide. Those are the types of things now we can solve with our chart solver. Here's a notebook that if you guys are interested in looking, and the goal for us is to really unify a lot of these different solvers and provide you with a seamless interface to really do end-to-end photonic design. That's basically it. There's a lot of other things I would have loved to cover, but I just wanted to give just a brief overview of all the different things that we're working on. And we're constantly building products and leveraging our GPU acceleration to provide you with not just like really well integrated solvers, but also solvers that are really fast. That's it from my side, and I'll pass it over to Tyler.